Okay, so welcome to our systems engineering course. Today we're going to cover chapter 3 on conceptual system design. And these are the elements of that sub-process. And this is where we really get into the mechanics of applying system engineering concepts to the craft of product development or system design. So the first thing that we're going to be talking about is how to identify problems and translating that into a need. So usually people, clients, internal or external will come to you with a problem. That's a good thing that they're coming to you to solve the problem, and hopefully you can do that effectively. But not all problems are well articulated. So you have to have a methodology to distill from that idea of a problem into a real need that eventually you can translate into system requirements. So we're going to be talking about that. And part of this conceptual system design phase is also starting the system planning elements, and I'm going to be discussing how that couples into the program management part of the activity, which is not the real focus of the course, but we always recognize that that's a parallel activity that is going on toward more of the business care about on the process. So again, from the need, the next big thing is to develop those system operational requirements, keeping in mind sustainability aspects. So a big part of what we're going to be talking about is the maintainability concepts, and that entails a host of elements such as the concept itself, the flow, the policies, and you'll see how we articulate that. Then we also have the identification and the prioritization of technical performance metrics. So we're going to show you a tool to do that, and when you use it in your next project, you're going to have this tool made available to you via Canvas. The tool is an Excel spreadsheet that helps you prioritize technical performance metrics and according to how you are using them to respond to the different needs. So it quantitatively highlights what's important, so you can use that information to prioritize, because everything may be important, but not everything is equally important. So how do you make a distinction? So this tool helps you with that. Then we're going to get into the functional analysis of systems, which is not, at this point, is not an architectural analysis yet. So before we even get to an architecture, we need to understand what is the functional view and the functional flow of the system. What functionality depends on what functionality follows other functionality, and things like that, and how we do that recursively with traceability as we traverse the hierarchy of the system. So the hierarchy of the system starts emerging, and eventually to a logical architecture and also a physical or geographical architecture, which may or may not be the same. Many times they do coincide, but that's not necessary. And then once you go through all these steps, you have enough information to put together a very important document, which is a system specification. And we're going to give you a specific outline developed by INCOSE, and again, INCOSE is the equivalent of IEEE for systems engineering, so this is not something made up or anything like that. This is actually a standard way of developing a system specification in a very easy to use outline or questionnaire format, which you can simply use and adapt to your very own project, but succinctly address the points in the outline. And the more succinct a specification is, the better. So you want to be succinct, bullet points, single sentences, right to the point. People don't have time to read fluff, okay? We just need the information. People are very busy. So that's not the point. The elements of the specification are very rich and diverse in nature, meaning that the outline is very long, but and that's because everything has been broken down to very detailed and simple elements that you can address almost as a questionnaire and get your specification done. But it's very important. And then at the end of this part of conceptual system design, and after you have a specification, the culmination is a review, and we're going to talk about what are the elements of good reviews in terms of stakeholder participation and what that brings to the table. So that kind of is a summary of the chapter. So let's start talking about problem definition, what it is. And formally, a problem definition is a comprehensive statement of the problem in both a specific qualitative and quantitative terms. So, and we have elements to address those two legs. The qualitative part in terms of functional system requirements, and then the quantitative part in terms of the technical performance measures. So we already have something to address that. And the flow, the thought process here is that, as I mentioned, there is a want, there is a need. And again, most of the time, because normally our human nature is not crisply rational, and it can be clouded by emotion, wants and needs are intertwined. We don't know how to really separate those, okay, from a technical perspective. So a need analysis helps you with that. And for example, a good litmus test is that if something is necessary, people are going to be willing to pay for it, okay? And that's a way to attaching a cost to additional features and requests and things like that help people step back and say, well, do I really need this? Okay, that's just an example. But once you understand the needs, you're in a good position to articulate system level requirements. So what is the process of analyzing the needs of a system? So first, these are questions that can be, and they're obviously not comprehensive. I'm sure that you can come up with additional questions. There may be overlap with additional questions, but this is a set of what I find it's a good set of orthogonal questions, meaning that there is not a lot of overlap between them. And as you are thinking about your own system, you can start asking these questions and discussing with your partner, because you're going to have to go through all this process in the next project, discussing with your partner and then trying to capture the essence of that discussion. So questions such as, what is required of the system in functional terms. So what does the system need to do? What are the specific functions? And you're going to see that once you have a list of those, when you put together the functional flow diagram, that diagram, crafting the diagram forces you to think not only about the functions, which may be a disorganized list at this point, but that's progress, that you have a list. But then the functional flow diagram is going to force you to put a sequence, a behavioral sequence to that set of functions. The other important questions are, now that you have functions, what are the primary functions? And what are the secondary functions that may depend on other functions? Again, all that, once you have, or you start getting insight into that, because a lot of these exercises are insight developing or seeking thought processes. It's just a discipline to help you and guide you to gain insight into the system, so you have a clear view before anything gets designed, before technologies get committed, before monies get spent, and overall the process of product development is more efficient. So what are the primary functions? What are the secondary functions? If you are looking into a system that already exists, sometimes you're developing a new system, sometimes you are improving upon a system, and then the premise is that if you're improving upon something is because there is a deficiency or something that you want to improve. So it must be important to be able to articulate what that is. And then you can also start bringing in elements of time. So there is always any type of productive endeavor is in the context of time. You know, you have a deadline, somebody wants it by some time, and that's driven by different factors. Most of the time, those are driven by business factors, budgets, strategies, product development or product launching, plans that a company may have. So it's driven by something. So, but it's important to then start putting the context of the timeline and layer that on top of all this insight that you're gaining. Equally important is to start understanding the environment in which the system must be operated. So where is the system going to be deployed? What does that environment look like? And also start asking questions about the usage mode of the product or project that you are about to develop. So heavy usage, moderate usage, something seldomly used. Those type of insights are important. So this is like a minimum set of questions to start developing that insight, because usage mode helps you later on address reliability, things like reliability requirements, and also the maintainability aspects and the serviceability of the product. So this is the minimum need analysis. So what is a need analysis? It's basically sitting down with the key stakeholders of the project and brainstorm these questions out until you can get very concise insight and answers to these questions. Okay? So let's look at a diagram, sort of a timeline diagram of this conceptual design exercise that we're talking about. We just talked about the definition of, or started talking about the definition of program requirements, of which need analysis is a part. And what's going to emerge from that is what is called a program management plan, which we are not going to be responsible for. You just have to recognize that there is an entity called a program manager that cares about these things. But the path that we care about, that we're going to be emphasizing and diving into, is this top box over here. We're going to spend a lot of time in this top box, which is the development of technical requirements that eventually will lead to a system architecture that is both logical or functional and geographical or physical in nature. And that's going to lead to this system specification, which in COSI calls type A. And you're going to have to develop a specification as part of your second project. And once you have that, we achieve what is called in systems engineering a functional baseline. Something that what we come up with will be different and will evolve, because we're not trying to be super rigid and dogmatic in saying that, well, nothing can change. That's not realistic, okay? That's not realistic. Something that the Agile methodology has shown, and if you go back and read things like the Agile Manifesto, is that flexibility and discipline are not opposite to each other. You can have flexibility with discipline and sort of get the best of both worlds and have a great product development methodology. But you do need a baseline, something that you can refer to and evolve into what the product is going to be eventually. We also recognize that, again, in this bottom leg, that's sort of the program management part. But we're going to focus here on developing the development of the technical requirements and system architecture, and then the system specification. And armed with that, you go into the next step, which is the actual preliminary design, which is the next chapter. And that is part of the program implementation. So that's how it fits from a timeline perspective. So let's keep going and taking a more detailed look. We did talk at length here on problem definition, identification of need. What do you do next? Now you're ready now to do the first set of activities that can be considered system level design, conceptual, but system level design, and part of that would be feasibility analysis. Because you will come up with perhaps options, different options on how to address these needs. And any option that you come up with is predicated upon existing research, existing technology. So we have this here as an input to that process, to highlight that it is very important. One of the best things that you can do to be successful at coming up with new products and addressing needs is to have a good general awareness and a sort of disposition to understand what is available. Because, and this doesn't mean that you have to know everything, you just have to be technically competent, aware of what's available, technologies, knowledge, research, at a level that allows you to say, we may be able to use this to address this need, but then you have to get confirmation. So that's the actual feasibility analysis and feasibility studies. But if you don't know what you don't know, you cannot go and get the knowledge. So the most dangerous thing that can happen is that you don't know what you don't know. There's nothing you can do about that. So always, at least, know what you don't know. There is a subtle difference there, but it's very important. Because knowing stuff takes time, and we're busy. So you cannot really know everything. But you can be aware of what you don't know so you can go and learn it when necessary. That is a life skill that is very important, and as more technologies become available and things become more complex, that is a very important professional skill that you need to acquire and maintain. So hopefully we're bringing that to the forefront as an important skill to have. So here the system requirement analysis is really sort of the meat of this conceptual design phase, which is coming up with the operational requirements. The maintenance and support concept, very, very important, because we're talking about a system that is important throughout the life cycle, and most of the life cycle is not the design. Most of the life cycle is whatever it is that you design. Most of the life cycle is selling that thing so it can make money. Okay? So, and if you are going to be successful at that, then you need to have a plan to maintain it and support it throughout that part of the life cycle in a way that is congruent with the business plan. But why do you need to worry about it now? Well, because more than likely you will have to put hooks and features as part of the design that may not be part of the user experience except when maintenance is required. So it may be a secondary function. You can see it as a secondary function, but it still needs to be considered. How you maintain it, how you support products. And we're going to see it again, how we come up with technical performance measures with the tool that I mentioned, the spreadsheet which has a name, and the functional analysis and allocation via functional flow diagrams, looking at trade-offs until you have a system architecture. Then again, you go to the specification and the review. So that's the chapter again in another view here. So we just talked about system feasibility analysis. What is that process? So again, all these are outlines of thought processes for you to follow and procedures so you have guidance. How do we know if a system is feasible? Well, first of all, we have to understand the mission of the system. And the wording, as you read the book, you may encounter that the wording of a lot of this terminology is like this, like mission and things like that. But remember that this came from the defense and aerospace industries. So they think in these terms. You know, a system has a mission. But that the reason that's good is because it's very clear, concise, and crisp. What is the mission? That's what the system must do. And it must do that with certain performance. And certain performance and physical parameters. It must, and they all not need to be two-sided parameters. They can be single-bounded parameters. We can say the system shall weigh no more than so many pounds, and that's okay. But that gives a very clear directive. The usage of the word shall is a strong directive that there's no deviation. It must. So there is a message of compliance there. So physical parameters like that, or performance parameters. The system shall not consume more than so many watts. There is a directive of compliance there, which if you are not there, well then, if that's really a shall, and you cannot do it, then that's not a feasible system. Because these are the strong must-haves. And it forces you to think about what's really important. Because if for some reason it cannot be done, it may be that someone is asking for something that is not possible. I don't subscribe to the thought that, well, if you try hard enough, everything is possible. No, there are some things that are not possible. And you just fail, and you fail quickly and move on to the next opportunity. Okay? So, but if you tell someone, look, what you're asking for is not possible with, the money that you're willing to spend, in the timeline that you're willing to give me, and they go back and say, well, no, maybe we change that. Then that wasn't really a need. That specific requirement was not a need because it changed. So it forces you to have that discussion. Part of the feasibility also is understanding where the system is going to be deployed, if it's going to be distributed, how it is going to be distributed. The operational life cycle, again, everything that we do is in that context. Utilizational requirements, I did talk about that. How is it going to be utilized? What's the user experience? These days, that is a big ticket item, the user experience, mainly when you have user interfaces and graphical user interfaces and software. There are people that sole function in life is to design user experiences and user interfaces, and they are not engineers. You don't want engineers to do that, believe me. We're too practical, and what we find easy, most people find cumbersome and hard. So there are people that are user experience designers, and that's a valuable addition to any team. Effectiveness factors and environment, but specifically to effectiveness factors, what we're talking about here is, for example, availability of the system. The system must be up what percentage of the time? What percentage of the time must the system be up? And that may direct you to how you design things like perhaps redundancy, reliability. What type of components do you choose to achieve reliability? How you put them together to achieve certain reliability? What things do you put in the maintenance concept so that if the system is down, it can be brought up quickly? So all these items are important, and they start shaping what the system is going to look like. So questions to help you do that are questions like this. What is the anticipated type and quantities of equipment, software, personnel, facilities, etc., and where are they going to be located? So general questions like this, how the system will be utilized, for how long, the environment of the operational site, and again, how the system is to be supported by whom and for how long. These questions lead into the maintenance and support concept of the system. So let's talk about that. What is a maintenance and support concept of a system, and why is it important? These are the elements of a maintenance and support concept. We need to specify the levels of maintenance, and we'll go through a conceptual example next. We need to articulate and specify repair policies, which means what type of repair do you do, at what level, and by whom. So that will tell you about the organizational responsibilities. What are the elements that you need to have in place to support the maintenance? And then how do you measure that you are doing what you say you would do? So if you specify that at this level of maintenance, the cycle time for this type of repair must be 3 hours, that is an effectiveness requirement. So you may have to do your design in such a way that that is possible. Okay? You may have to do your design in a way that that's possible. And if you say also that the turnaround time is different from the cycle time, because the turnaround time includes wait time at the facility, must be a day, then you must have enough personnel, enough infrastructure, and you must be able to anticipate a number of units arriving at this facility, but you must have enough infrastructure and personnel to be able to address what's coming in and have a turnaround time on the day, given that the cycle time of the actual repair on average is 3 hours per se. Okay? And it gets into quantitative elements of the analysis. We are focusing here more on the qualitative way of implementing and thinking about this, but in subsequent chapters, which could be a more advanced course, the book does get into quantitative ways of calculating. For example, if you have X number of units arriving and using queuing theory, how many stations do you need if you want to get those to wait or no more than a day of turnaround? So you can actually, there are ways of calculating that. There is also software to simulate things like that. So those are examples of effectiveness requirement, which again tells you, what type of environment do you need to have in this maintenance and support concept. So let's look at a specific example. So to develop a maintenance and support concept, I expect some type of diagram like this. Okay? Maybe it doesn't have all the elements, but I want to know that you thought about it and that you made a pretty diagram like this. Okay? So let's say that we have a system here. And again, this is a made-up system, nothing in particular. And this system, we already understand at this point the operational environment. So this is a system that can be deployed at some ground facility. It can also be deployed in a ship, or it can be deployed in an aircraft, okay? So that's what it is. That's what it's going to live and perform its mission. We're going to call that the operational site. And we understand that it's not just one site, 3 different sites with different characteristics. And that has its own implications. But we can start articulating maintenance and support elements and policies. For instance, at the operational side, we can say that we're going to be able to do on-site corrective and preventive maintenance. But at what level? Only critical items that are pointed out as needing corrective and or preventive maintenance via built-in self-test capabilities. So now you have to worry about part of the requirements of your system is that the critical elements must have built-in self-test. So how are you going to do that? Now you have to build that into your hardware, into your system, into your software. That becomes now part of the requirements, and that's why you look at this early on. But remember that the concept is much more than just the design. You're looking at the whole enterprise, the whole infrastructure. So what type of personnel are we going to need? Well, if this is just pushing a button so that some display tells us good or bad, then that's pretty low skill personnel. So we know that. Now, for some reason, part of the system is that we're going to have, it makes sense, to have this intermediate maintenance facility. So we can say, well, in this intermediate maintenance facility, we're going to do corrective and preventive maintenance at the subsystem level. So now, not only the system is going to, at the side, the system just says good, bad, replace this, replace that. But here, we're going to be able to go inside the subsystem, and we're going to have dedicated test and support equipment. So for example, on the operational side, there is no mention of equipment. And that's why everything is supported via the self-test or diagnostics capability, which is part of the design of the system. But here, we're going to be able to go beyond what the system and subsystem can tell us because we have dedicated test infrastructure. And because we have that now, we can say that the personnel has medium level skills, and this acts as a field shop facility where some components are staged and the some repair can be performed. Then on the left here, we have this other facility, which is the factory. So here's what we manufacture in this system. So we certainly can do everything here. We can do any type of detailed maintenance. We can overhaul a system. We can do calibration, which is something very expensive because normally things need to be traceable back to the National Bureau of Standards. We start supporting the supply. We have factory level test equipment, so more comprehensive test equipment. and we can say that the personnel in this facility is highly skilled. And finally, we have the component suppliers, because we're not making everything from scratch. We are using components. There is a supply chain. So now that you kind of understand the differences between these different facilities, let's very quickly look at a couple of flows. First, the maintenance flow, which is the dashed lines, dashed arrows. So here at the operational site, we have, via this built-in self-test and diagnostic capabilities, we need to be able, or the system needs to be able to provide enough information such that the people involved with the system at the operational side can make a decision according to some repair and maintenance policy, whether to send it to this intermediate facility or whether to send it directly to the factory. So these two arrows here highlight a decision point. And then it may be that it comes here, it gets dealt with effectively, but maybe that was still not the right call. And the intermediate facility still cannot fix the problem. So it needs to go back to the factory. And again, maybe they can deal with it. Maybe a component is defective, and that is a component that you may discard it and put a new one in, but if it's a valuable and expensive enough component, maybe that needs to go back to the supplier for exchange or repair. So that is the maintenance flow, which is followed by a supply flow. Component suppliers can supply both the factory or this intermediate facility directly. That's important to know. That is a supply chain aspect that needs to be made part of the infrastructure. The factory clearly is going to supply the intermediate facility, and then the intermediate facility is going to supply the operational site. Notice that the factory does not send anything back to the operational site, even though it does receive goods from the operational site. That is a logistic aspect, a characteristic of the logistics that we are defining through this diagram. So you can see that we, and depending on the characteristics of shipping and you know how things need to be deployed, packaging, a specific packaging may have to be designed for this. So that's why it's important to worry about all these details, because if it's done without planning, that's where delays occur. So here's a chart which essentially captures everything that I said before. So make a note to read this. So as I often do, things that are very busy like this, I don't like to read them to you. I don't find that effective, but I do want to, they do capture what I say, but they're here in a structured manner that these are good candidates for you to go back and study in detail. So part of the maintenance and repair policy flow can be a diagram like this. Here we have the deployment site. Here we have the intermediate maintenance facility, and here we have the factory with its calibration laboratory. So this gives you an example with some effectiveness measures that you can make available as part of the exercise as an exhibit that you thought about these things. So let's say that at the site we can have unscheduled maintenance. So anything that is not scheduled maintenance is because it was triggered by a fault. So, and we talked about the availability of built-in go, no-go type of diagnostics. So we can, let's say, provide fault isolation to a unit in the system. So some box in the system, okay? And let's say that this can be, this capability exists in units A, B, C, D, and or E. If a fault is identified, then if you follow the flaw that we just discussed, then that goes to that intermediate facility, which can fix it. Which can fix it for unit B, but for the other ones, so basically it deals with it. For some units, it deals in some manner. For example, if it's a power supply, then we know it's very complex. It happened as an example. If it's a power supply module, then it goes directly back to the factory. They don't even look at it because for some reason, maybe this is a very complex unit. Some other things, such as units A, B, and C, if they had to deal with it, they have to be recalibrated. So they go back to the calibration lab in the factory. Some other units may come from a scheduled maintenance. So they taken out, they get replaced in the operational site, they get sent for a scheduled maintenance at the intermediate site, and again, from there, they can be sent for calibration. If calibration is due, it may be that you fix it, but it still is not due for calibration, so you don't necessarily have to go back to the factory. But in the case that that happens, you do have to send it back. And then you have support factors or metrics here. So as an example, this is not comprehensive, but some of these elements, mean time between maintenance. So we don't want to, we want to be able to go 175 hours without any maintenance. If we find that we are maintaining this more often, that start eating into our support budget, and we have to, why is that? That is an issue. We also want mean time between failures to be 250 hours. So that those are specific targets that can drive design decisions in the design of the system. We want to be able to deal with the system, so the average M, 30 minutes. So we want to be able to do whatever it is at the operational site in 30 minutes. In and out, 30 minutes. If it takes us longer, that's not a good thing. So we have to make sure that the system is designed so that is possible. So you start getting the idea for the different effectiveness factors down here at the different sites. Calibration lab, intermediate facility, as well as the factory. Then you can see here in dashed lines the flow of spares, because the field needs to have spares, the intermediate maintenance facility must have spares for itself, as well as to pass to the maintenance site. Even things like transportation time is specified here. So we can see here transportation times to get from the factory to the intermediate one is 2 weeks. To get from the intermediate to the operational site is 1 week. So all these things are important from a logistics perspective because they may have an implication in the actual design. So make a note to go back and study this because it's another busy chart, but again, pay attention to the different supply factors. So, turnaround time, what type of facility, for example, the calibration laboratory needs a clean room, turnaround time, 14 days here at the factory. So just go through everything and look at all the possibilities through the lens of this being examples. These are not comprehensive. These are guidelines, but it is the challenge and your job and the interesting part is how to actually come up with what is relevant in your main to your own product. All right, so now let's switch gears and talk about technical performance measures. And I did say that we were going to expose you to a tool that makes the exercise of prioritizing technical performance measures in a quantitative manner, it makes it easy, okay? This tool, and by the way, technical performance measures are the measures of the design-dependent parameters. So, in other words, these are how you measure the quantitative parts of the design. This tool is called a house of quality. It looks like that, so it looks like a house. And it comes from the School of Thought of Quality Function Deployment, which is part of continuous quality improvement, a bigger set of philosophies for the development of products and the manufacturing of goods. So this tool has several parts. Here is the needs, and the needs are what is it that the system needs to perform. And the tool, as you'll see, has a facility for ranking the needs. You have to go through that exercise of ranking, and this tool iteratively helps you with that. Then here, the design attributes are the hows. They're also called technical response. If you have these needs here you populate how you're going to respond to the need from a technical perspective or with a design attribute. And basically you would be putting information in these cells over here. Then at the bottom, for each of the technical responses, there are going to be the technical response measures, which is how do you measure that response is addressing the need. Okay? Then over here, you're going to have an opportunity to highlight the interrelationship among the attributes. So technical correlations between the different attributes, because this allows you to highlight technical synergies in the addressing of a need by multiple design attributes. So those are the main parts, okay? Then this part over here has to do more with program management and marketing, which we're not going to really go into that, but we are going to care a lot about this area, this area, this one, this one, this one, and this one. So that's the gist of this tool. And again, you will get for your project, you will get an Excel spreadsheet, which is already populated with the algorithms to do this. As you'll see next, I have an actual example for that. So let me show you a very an example of how this gets used. This is a real product which mission statement has been articulated as succinctly as possible. This is succinct, okay, even though it's wordy. As succinctly as possible we have articulated in this manner. It's a real product. And what is in bold is what was determined to be the need of the system. So let me give you some time to read that. Read that because then I'm going to show you the house of quality that corresponds to this. So you did the need analysis, and now you are in a position to highlight the needs and go to the house of quality to get the technical performance measures. Let's see how we did that, but first read this so you can then understand the next slide, okay? Yes?
Is this an example of a problem statement, or is it kind of just or is it more that is it not safe, like, is it a problem statement, or rather is it not succinct enough to be a problem statement or representative of just customer needs?
Is both. It's a problem statement leading into the need analysis in this. So again, these processes are not dogmatic. I mean, there is flexibility there. You have to adapt it to your own. For this product, this made sense. Okay? So everybody has had a chance to read through that? Okay, so then this is a little hard to see, but this is a screenshot. This is a screenshot of the actual spreadsheet that you're going to get. This is just a screenshot right out of the computer. It's still a little busy, but it gives you a better idea, okay? Because only cells in white is what you populate. All the other numbers and priorities and weights and things like that that help you prioritize and make decisions, and also identify what are the challenging points, because if something is very important but it's very difficult, then you prioritize it from an execution perspective. You want to start working on that right away. You don't want to delay that. So it allows you to get all this insight and validate them in a numerical fashion, in a quantitative fashion. So there is no ambiguity. So for us engineers, that's very valuable, okay? So, so here we have the needs and the ranking right out of the statement. So these are the things that were involved in the statement. And then here we have technical performance or technical design attributes that allows us to address the need. And one design attribute can address multiple needs. And a need may need to be addressed by multiple attributes. So you have to think about all these cells one by one. Again, it's an exercise of insight development. Then let's look at this legend here because it's not binary, okay? There are degrees. For example, there are degrees of strength of relationships. And we have strong relationships, moderate relationships, and weak relationships. So we can also specify the level of strength of a relationship between a response and a need. For example, it may be that a particular response addresses some of the need, but it's just a small partial response that does just a little bit for that need. So that's not a strong correlation or a strong relationship. So you populate that with that symbol. And these symbols basically are drop downs from the cell. So you basically click on it, it drops down, and you pick whether it is weak, strong, moderate. But you go through each of the cells and think about it. That's the value of the tool. Here, you can also it may be that things don't have just a relationship, but there are things that need to be, or needs that need to be minimized or maximized. So back to those single-sided type of specifications, so you can put that instead. So here we have something needs to be minimized or maximized, or something needs to be right on target. So you can also specify that. So that goes into the difficulty of the implementation of something. Having something right on target is more difficult than just meeting a single-sided constraint, being under or above something, a limit. Then over here you can have those cross-correlation relationships, okay? You can highlight negative correlation, which may mean that as this technical response becomes more prevalent, it works against this other technical response, okay? So, you need a long battery life, but then you need your device to be very small. Well, that's an inverse correlation. They fight each other. So you need more battery life, you just put a bigger battery. But you need a very tiny device. Well, what do you do? So it allows you to highlight those conflicting requirements that more often than not are the ones that you end up spending a lot of time on. Because when everything lands up nicely, that's no problem. But when you have conflicting requirements, those are tough to address. So this allows you to, early on in the process, highlight these issues. You can also have very synergistic technical responses. Strong sometimes, okay? So you can highlight those here as well. So basically the way this works is this one here is the intercept of, let's say, you have a relationship. But this allows you to look for those and go one by one, pair by pair, thinking about whether there is that relationship. So here would be the intersection of this one over here, and this is the interception, so it would be with this one over here. And it is a strong positive correlation. Frankly, I cannot read this here, but when you get the slides, you'll be able to read it. So again, the idea here is go back, get the slides, and study this in the context of the previous slide, which is the problem statement and need analysis. So this is a great tool. You'll get that spreadsheet. I'll push it out via Canvas, and you have an opportunity to use it for your specific project in the next project after the break. Okay. Now, this exercise of the house of quality has to be done recursively at all levels of the system until you traverse the hierarchy that you have set up for yourself, the subsystem level, until you get down to components. You don't have to do it for components, but the point here is that you have to do it for subsystems. And then each combination of address need and design response can be addressed by a subsystem. And if that's what happened, then you need to do a house of quality for that subsystem. Do a need analysis, do a house of quality, and what emerges from that is a family of houses of quality with built-in traceability of requirements. Okay? So, just to highlight the fact that we have to do this also at the subsystem level as we traverse and the hierarchy emerges. So once you have this list of technical responses and you have visibility into the technical performance metrics or measures, you can start doing functional analysis and looking at how these responses are going to shape the functionality of the system. So you start getting really in a position to articulate the functional requirements both quantitatively and both qualitatively and quantitatively through the technical performance measures, and start putting together the top level system architecture. So the requirements are the functional architecture, but then the structure, you're going to start to be able to put together the structure of the system, geographical or physical. And again, this may or may not coincide. Many times, I would say a lot of the time, they coincide. That should make sense. But just keep in mind that that's not necessary to have a good system. It may be that the best thing for the system is that those don't coincide. But by following this process, you'll be able to come up with that conclusion, minimizing ambiguity. That's all we're trying to do. How will we follow a process, sort of a roadmap to not get confused or paralyzed by analysis and be able to move forward in our thought processes so we can get to where we need to be. Okay? This functional analysis is done best, once you understand the functionality, is done best by a functional flaw block diagram. And this is a standard systems engineering type of diagram. This is not a functional block diagram. It's not a schematic. It's a functional flow diagram. The flow is a key word because it highlights the flow of functionality and behavior rather than how things are connected. This is not a connectivity diagram. It's a functional flow diagram. So we can have our system. Behavior may be that we have function A, and then we have function B. But from function A, we also have function E. After function E and B, we go into function C, from which we go to function F after also E has completed. And we also go to function D, and we go back to function A. More than anything, this resembles a state diagram more than a connectivity. So if you recall state diagrams, which are very useful because a lot of embedded software is written as state machines. It's a great way of writing. The nice things about state charts and state machines type of as a way of describing behavior, the nice thing is that you can target software with the same diagram. You can target an implementation of software, but you also can target an implementation of digital hardware. So if you require a lot of performance, then maybe you have to do your own hardware, but maybe just doing software, but it's the same description. So you have, for those of you sufficiently familiar with object-oriented development, we have something that is very attractive from object-oriented development, which is polymorphism, right? We have a single way of specifying something, but then we can have multiple implementations. And that's a wonderful thing. Highlighting here that this is also hierarchical in nature. So this function E may have its own second level functions here, and this box over here, 5.5, may have its own set of third level function, just like you can have hierarchical state machines and state charts. You know, once you go into a state, that could be a super state, which you come in and out of at the top, but that super state may entail its own state machine implementation. But thinking about all this up front is the key to getting products right, and as I like to say, doing the right things, and also doing the things right. Okay? These diagrams for function flow can also be augmented and clarified with logical connectors. So this is just to show you that you can be more explicit and have and logical connectors here, for example. So after we perform this function, we're going to perform this one and perform one of these two. What's the benefit of highlighting this information with logical connectors is that you start getting visibility into the available resources. So let's say, and remember these are complex systems, so it could be, it's not inappropriate to assume that, let's say, one of these boxes is going to be implemented by a whole processor. But, so here you have this processor doing this, and here you have two functions that you know you'll never be doing together. So you can have a processor do this, but then now there are two functions that you can assign to the same processor because they're not concurrent. So it's going to be doing one or the other. But you cannot assign the same processor to do all three of this, because sometimes you're going to be doing this and you're also going to be doing one of these functions. So again, being able to highlight concurrency, you start getting visibility into how to best schedule the workload of different resources in the system. This may be a system where there are no processors, it may be people. But again, resources are resources from a system engineering perspective. We want to be able to optimize the usage of resources in the system. So adding connectors is a great way to start gaining that insight. As we start wrapping up the chapter, hopefully you are seeing that by doing this, all facets of the system design and development, support, and even phase out, which are the elements of the life cycle that we discussed in the previous chapter, start being looked at proactively upfront. And you have an opportunity to really recognize and define everything that is necessary to be successful. So planning in complex endeavors is very important. Even issues such as packaging, because you start looking at the physical structure, sequences of activity. By knowing what's more important, the priority, you can start organizing and scheduling activities in a way that also optimize cash flow deployments, and you don't have, so you don't waste capital. Also, interfaces. That is very important. Being able to highlight interfaces between functional entities early on, so that way if you set the interfaces early on, then this is something that System Composer will allow you to do, is define interfaces and set them between the different blocks. If you define the interfaces and the behavior of those interfaces, then teams can go and address the actual subsystem or block in whichever manner they want. And as long as the interface behaviors are respected, then you know that things are going to be integrated appropriately. So as you come up with this functional baseline of the design, you also are going to get visibility and insight on reliability requirements. You may have enough information to feed into the working of a reliability model, which is could be a whole course in itself. How do you build a reliability model of something which is predicated on not only the behavior and the functionality, but also materials, how material science affect the reliability model of systems. So there are people that's all they do. They do reliability models to tell you what type of reliability metrics you need to follow at the component level so you can achieve certain reliability metrics at the system and subsystem levels. Maintainability requirements, you'll be able to get insight on human factors, what type of human resources you need, and of course we talked about the supportability. So you have this functional baseline starts being transformed to the allocated baselines, which means that in this baseline you're already planning things and allocating resources, both human capital and functional resources of the system, to what eventually is going to become a product baseline, a product that you are going to design. Remember that all we're doing here is planning. We haven't designed anything yet because we didn't know what we needed to design. How can we know if we're designing the right thing if we are not asking and answering these questions? we may end up designing totally the wrong thing. That's what we're trying to avoid. It happens all the time, okay? Sadly. So, I started talking about this, about the communication interfaces, and which helps you define how you separate, if necessary, the functional architecture from the physical architecture, because these interfaces, both logical and physical, is what connects the different elements of the system. So the way to do that is via interfaces, okay? Because interfaces is what binds the logical structure to the physical structure. You have to, whether something works together logically, but it may not be together physically, if you're going to achieve that, then you must have some type of interface or connection present. So just to emphasize what I just said, the definition of the interfaces early on is very important at this point. So as you start getting this architecture together, logical and physical, from all these answers that you got on the what's, the hows start emerging. And once you start dealing with the hows, you are in a very strong position to do good design, to actually put together documentation on how something is going to be built. That's what a design is a set of directives to tell the factory how they're going to put this product together. And then you can have a architectural diagram. Now this one does imply some type of connectivity and communication interfaces. It contains that, but more, because you can include as part of the system operators, software and facilities, but equipment, actual hardware. So let's say that this equipment has 3 units, and this unit has 3 assemblies. So these are actual physical things. This is an actual structural diagram. This is not a functional. So do notice the difference of this between the functional flow, but it was the functional flow that gave you enough insight to put something like this together. So you also have to have this type of documentation. All this documentation is eventually going to make it into the spec. Once you get to this point, I want to highlight that it is possible that if the team is big enough, if things were structured from a human resources perspective differently, or maybe the same team came up with different design alternatives. Maybe you only have one alternative, but maybe different alternatives during this exercise, different alternatives came about. Well, you have to get to this point where you have all this documentation for all the alternatives, and you do system trade-off analysis between the alternatives. Maybe you start merging alternatives to come up with a winning strategy. But here's a sort of a recipe for system trade-off analysis, in which you can look at different alternatives, define the analysis goals for doing the trade-off analysis. Which data are you going to be collecting? What type of this is the part where you actually start trying to generate data via simulation. So simulation becomes important, trying to simulate instead of build things, because building things takes time, takes a lot of time, and it's much more expensive than simulation. So how do you simulate and take advantage of that technology to come up with data that allows you to evaluate different alternatives and do trade-off analysis? And then always checking for feasibility, and then you get to the point that you have that system definition. You have a system definition, you're ready to document it. This is the outline for a type A specification. You're getting this. Again, how do you adapt it? This is very comprehensive. Not everything may be applicable to what you're doing, but you have here everything, usage, and use it rather, in a way to help you be successful. This is not just because, don't do things because somebody asks you to do it, or because just to do it. Do it because you find value in it. And I'm telling you, there is value in going through the documentation process highlighted here. So almost in questionnaire format, very comprehensive outline of the type A specification for systems. Use that, and after that, then you are ready to review. This may take days. You know, these reviews may be you on your partner for the next project, you know, drinking a cup of coffee and talking about it. This may take years, depending on what the project is. This process may take years. It may involve hundreds or thousands of people. So, and that's a key thing to recognize, that this process, this approach, is massively scalable. It's beautiful in the sense of how scalable that is. You'll see that you'll be able to follow this process with the same rigor between two people as it can be followed by a huge type of enterprise and project that is taking multi-years and thousands of people. So that speaks very well for how sturdy the approach is. So reviews are important. Reviews are important because it provides a formalized milestone, sort of putting a stake in the ground that, or you did all this work, and it allows everybody to come together through the documentation of the specification, and it provides a common baseline for everybody involved, the key people, the stakeholders. It is during these reviews that interface issues get resolved, so that past this point, the interfaces are set in stone, so that everybody can go and perform in their own boxes and do and optimize there as they see fit, but by respecting the interfaces. Then when you integrate everything together, everything is bound to work. It also provides formalized records of everything that was the decisions that were made, and so it provides higher probability. So nothing is guaranteed, but I am telling you through my many years of experience that this is a process that provides you with the highest probability of success, whether it is on a big project, a huge enterprise, or your project that you're going to be doing in this course, and your senior project next year. Okay? So, any questions? Anything that you want me to go back to? Yes.
The kind of works with the, I guess, kind of like the final extensive version that you showed of like the requirements and all that, like the final requirements page. I think there's like 2 or 3 slides back. Yeah, that one. The system specifications. What, like, do you know, like, in terms of like, you know, like percentage or amount, what are we trying to show for our senior project of this diagram?
Well, so what I would expect you to do, okay, if I was your senior project advisor, is that you take this and in your team, you go line by line and then ask the question, how applicable is this? And have a discussion about that. And if you can have a meaningful discussion about that, say, well, maybe this is not applicable, then it doesn't need to be there. Then you distill that to what's applicable. Then you go back and you have a lot already because you've done everything else, right? Then you populate it with the knowledge and the insight that you gain comprehensively but succinctly, okay? Not like, this is not meant to be, again, this is meant to be something to help you rather than just to tax you. It's not supposed to be onerous. It's supposed to be to make it easy. So basically, you get this done. That's why I give the opportunity for people to do this for their senior project like now, because imagine you get here in September, you can hit the ground running because you know exactly what you want. You already have that product baseline, that functional baseline. You're ready to start designing and very quickly, and we are asking students to have something to show by the end of the fall. And this is something that gives you the highest likelihood to do that. Did I answer that question? Yeah. Any other questions? All right, so thank you very much. So remember, the video and the slides will be up shortly, homework for chapter 3, which will be due first thing next week. And next week we'll have the midterm, and then you will have a wonderful break, okay? I'll see you next week. Thanks.